Hi, this is Bob Westerveld. It's a pleasure to introduce today Ankit Disa. Um, Ankit has been at Cornell. Started out as a BS in 2010 and then went to Yale for his PhD, then returned to Cornell for a postdoctoral associate, and then this year is becoming assistant professor. He's going to tell us about a hot new area in condensed matter physics where you use intense light to actually create new electronic states and study how they work. So we're very happy to have him today. Ankit, thanks.
All right, thank you. Thank you, Bob, for the introduction. Hello, everyone. So sorry to those of you who were expecting to hear from Matteo Mitrano today. I thank him and the organizers for offering me to let me take his place, and I hope I won't be too disappointing of a replacement. Let's see. Thank you, for the introduction. My name is Ankit Disa. I actually have been in Hamburg doing a postdoc at the Max Planck Institute for the last several years, and I'm currently at what's called the Max Planck New York City Center for Non-Equilibrium Quantum Phenomena, and I will be joining Cornell. Going back to Cornell in July to start a new group. So what I'm going to tell you about today is work that I was doing and led over the last several years in Hamburg in the group of Andrea Cavalieri. And the image that I'm showing here in the background, I think, tries to capture the general idea, which is how we can use light to manipulate magnetic order, and in particular to create non-equilibrium magnetic states with desirable properties. And the way that we will accomplish this, as I'll tell you, is by exploiting the crystal lattice. So before I get into it, I want to first acknowledge some of the people who really helped make this work possible. I especially want to point out Michael Fechner from Hamburg, and John Curtis and Pranay Narang from Harvard for theory support, and the Keimer and the Oxford groups for samples, high quality samples. So let me start by explaining why the crystal lattice is so important and powerful as a way to engineer functional properties. And to do that, I have to introduce the materials that we're studying. Of course, we're interested in quantum materials, as I would say most people are these days, but more specifically, what I'm going to talk about are what I'm calling here correlated quantum materials. And what I mean by that are materials in which the electronic interactions, like the Coulomb-Hans crystal field interactions, all have energy scales which are on par with the kinetic energy. And so this leads to a complex interplay between the various degrees of freedom of the system. So the behavior of the crystal lattice and the electronic charges, orbitals, and spins are all closely intertwined. And if we think about the thermodynamic phases of such a material, instead of this usual free energy picture that we can imagine, where we have a simple system where the system can, let's say, neatly occupy some minimum energy state at low temperatures. Instead, in these correlated systems, we might imagine a much more complicated energy landscape. I'm showing you kind of a cartoon of that here, with a huge possible set of ground states and nearly degenerate phases because of the competition and cooperation between all these different degrees of freedom. Okay, and one of the big consequences of this interplay is an extremely sensitive coupling between structure and functionality. So let me show you a simple yet demonstrative example of what I mean. Transition metal oxides are a big common class of correlated materials. So let's consider one such oxide, strontium vanadate, which is very simple. It has a cubic crystal structure where the vanadium ions sit in the center of this cube, and it has one active electron that's relevant for the low energy properties. It lives in a vanadium D orbital, and the electrons can talk to each other by hopping through these intermediary oxygen ions, right? So in this particular structure, the bond angles are quite straight, so it's easy for electrons to hop, and the system is therefore metallic. Right? Now, if you look at similar compounds, all with the same electronic configuration, but with slightly distorted crystal structures from one another, you find something quite dramatic. So nominally, you would expect that all of these should have similar properties, but you will find that some of these are metals and some are insulators. And you'll also find that some are paramagnets, some are antiferromagnets, and some are ferromagnets. And these phase transitions all occur due to a relatively small changes in bond angles that essentially dictate the ratio between kinetic energy and Coulomb repulsion. You can think of it like that, right? And so this enormous sensitivity to external perturbation creates very rich and complex phase diagrams. And as I'm sure you all know, the phases and properties that you can find in these correlated materials are quite unique and can be potentially functionally useful. And these are some of the more famous examples: cuprates, nickelates, manganites, just to show you the complexity of these systems. And the fact that in some sense, regardless of the actual material that we choose, there always seems to be an enormous amount of complexity in the phase diagrams of these materials. And so this is something we want to take advantage of. And in very broad terms, what I'm interested in is trying to take a material that has some desirable phase or property and to tune it, right? And maybe you want to change the temperature at which the phase emerges. Maybe you want to realize a new type of a state that doesn't exist in the material. And so in equilibrium, you can do this by applying pressure or magnetic field or doping. But often still you have properties that are limited in a particular material, where maybe the phase that you're most interested in only exists at very low temperature or very high pressures or fields. So ideally, what you like to be able to do is somehow go beyond the equilibrium phase diagram. And the approach that I will use to try to do this is to essentially dynamically drive the material with light pulses so that we can push it into a non-equilibrium regime. And ultimately, this can lead to different types of behavior, which can be controlled on very fast timescales and often beyond what's possible in an equilibrium setting. And this has become an increasingly popular research direction over the last several years, with many groups working on this, including those part of the CIQM. And I think one of the reasons that optical driving is so appealing is that you can do something quite simple, which is to tune the frequency of light to match the characteristic energy scales of the degrees of freedom in quantum materials, the charge, orbital, lattice, or spin degrees of freedom. And this is somewhat obviously because this is how optical spectroscopy works, right? You change the frequency and you see resonances corresponding to these different excitations. But in the context of control and optically driving a material, it's also quite powerful, since you can take advantage of this selectivity, the fact that there are resonances, to address a specific collective mode that you're interested in, right? And so a lot of work has focused on this high energy side, directly exciting electrons, and trying to create non-equilibrium states in this way. And this has been a powerful approach. But in Hamburg and in my own research, what we focused on is actually to take advantage of what I talked about a few slides ago, which is this extreme sensitivity of quantum materials to changes in the crystal structure. And so what we've been trying to do is look at how we can use light to engineer the crystal lattice by resonantly exciting vibrational, so optical phonons, which lie in this few tens of terahertz frequency range. Okay, so what we do is we spend a lot of time developing high intensity terahertz sources so that we can achieve this kind of a control. And now we're at a stage where we can essentially create terahertz pulses across this whole range with peak electric fields on the order of several megavolts per centimeter. And what these types of fields allow you to do is drive atomic displacements that are very large, on the order of several percent of the equilibrium bond distance. And importantly, with these extreme atomic displacements, the response of the lattice then becomes highly nonlinear, and we can use this nonlinearity as a tool to access the new crystal structures and functional properties that we're interested in. Okay, so this is what I will be focusing on. So let me just try to describe how this works. Maybe you've all thought about this before and it's obvious, but what happens when we actually bring in a light pulse to resonantly excite a material? So a number of things will happen. The first thing that's obvious that's going to happen is that we're going to shake the lattice along the coordinate of the mode that we excite. And so remember, light is only going to couple directly to modes that carry a dipole, so we can only do this with infrared active modes. And so what this excitation does is lead to strong lattice vibrations. The atoms are going to shake up and down, and they're going to shake very rapidly. And on average, we're not going to actually have any change in the lattice, though if you could look within each cycle, you will see some different crystal structure. But in addition to this, if the excitation is strong enough, another thing that's going to happen is that the anharmonic interactions of the crystal lattice, so the fact that it's not a perfectly harmonic crystal, start to become important. And we will couple to other modes of the system besides the one that we excite. So in particular, we will be able to couple to Raman modes, which we couldn't directly drive with light. And in fact, what this particular interaction does, which is really one of the lowest order interactions you can have, is that it provides a force that pushes on this Raman mode from the IR mode. And because this is quadratic, this pushes in one direction. And what this does is that it means that in addition to driving a vibrating component, the crystal will have experienced a rectified average change to the structure, okay, as you can see here, that creates in this transient regime a non-equilibrium crystal structure, something that doesn't exist in equilibrium. And you can imagine something that looks like this. We start out with bond angle straight, and now we can create, for a short time, a distorted system. And so both of these kinds of effects can influence the electronic and magnetic properties of the system. And here I'm listing non-exhaustively some experiments that have been carried out that demonstrate the ability to change macroscopic properties through these mechanisms. What I'll be showing you is how we can build off of this type of work and try to go beyond it and work towards rationally engineering the crystal structures with light to achieve specific non-equilibrium functionalities. And so I'll show you two experimental examples about how this can be done, focusing on magnetism. The first is how we can induce a non-equilibrium magnetic order, specifically turning an antiferromagnet into a ferromagnet. And in the second, I'll show you how we can actually even extend this behavior to high temperatures to stabilize magnetism above the equilibrium TC. Okay, so in the first experiment I'll show you, we're going to talk about controlling antiferromagnetism, and let me just give you, one 30-second slide about why we would want to do that, right? So one of the reasons is that it's been kind of recently appreciated in the community, especially people who work on ferromagnetic technology, magnetic technologies, that antiferromagnets actually offer a number of advantages in various applications over ferromagnets, because they can be packed denser, they can be manipulated faster, they're more robust to external perturbations. And this could be useful for spintronics, memory storage, etc. But the reason that we don't use antiferromagnets as much as ferromagnets is simple. It's basically because it's very difficult to control the state of an antiferromagnet for switching. Essentially, we would require, in principle, a magnetic field that alternates on each atomic site so that we could switch from one type of domain to another. So the main question we try to address here is, is there a simple way we can control antiferromagnetic order using light in a way that is robust and fast? Okay. And so in this experiment, we looked at a model antiferromagnetic compound, which is known as cobalt fluoride. Okay. This is one of the simplest antiferromagnets you can imagine. It has a BCC lattice of fluorine ions, of cobalt ions. Each cobalt is surrounded by an octahedron of fluorine ions. And the important point is that normally the cobalt ions on the corner of the cube here have a magnetic moment that's equal and opposite to the one in the center of the cube. So it's a fully compensated C-axis antiferromagnet, has no net magnetization, and it's something that's been studied as an ideal antiferromagnet since the 50s. So the question is, if we take this, how might we go about manipulating magnetic order in the system? So cobalt fluoride has this interesting property that the orbital magnetic moment of the cobalt ions is unquenched, and it's essentially set by the octahedral environment around this cobalt. So this moment you can imagine as being dictated by largely by the in-plane cobalt-fluorine bond length in this material. Here, I'm just showing you a top view of this, and which shows you that by symmetry, the bond length in the center of the cube is the same as the bond length in the corner of the cube. Okay, so by symmetry, these two are equivalent, which is one of the reasons why you have a fully compensated antiferromagnet. But if we could somehow break the symmetry, we would be able to modulate the antiferromagnetic order. And one way you can do that is by applying a uniaxial strain along the 110 direction. What happens as a result is that one of the bond lengths is going to get shorter, and one of the bond lengths is going to get longer. And that will make the orbital moment on one of the sublattices larger and the other one smaller, creating, in effect, a ferromagnet that now has a net magnetization. And this magnetization is linearly proportional to the applied strain. This effect is known as the piezomagnetic effect, which is analogous to the piezoelectric effect that you'll find in ferroelectrics and other types of crystals like that. And this is really a potentially useful effect, because what it allows you to do is control both the magnitude as well as the direction of the magnetization by straining in one direction or the other, which is a useful tuning knob for magnetic applications. But of course, there are disadvantages, because you actually have to physically deform the crystal with a uniaxial stress. It's going to limit the amount of induced magnetization that you can achieve before, for example, the crystal breaks. And the effect will be slow, limited by acoustic timescales. So can we somehow overcome these limitations and emulate this effect with light without actually having to apply a physical strain? And the answer is yes. What we need to do is essentially mimic the types of distortions that come from uniaxial strain, which are these antisymmetric cobalt-fluorine bond distortions. And it turns out that these distortions coincide with the atomic motions of a particular Raman phonon in the material that has the same symmetry as this strain, which is the B2G Raman phonon. And what you can see if you look at the atomic motions associated with this mode is that you get the same antisymmetric changes in the cobalt-fluorine bond length from the two sublattices. But here, this is an optical phonon, so you're not changing the volume of the unit cell at all. Hence, you will be able to generate a magnetization, which is going to be proportional to the amount that you're displacing along this mode, but you're not going to be limited in the same way as strain by the elastic constraints of the crystal. And so the question is, how do we do this? You have to break somehow the underlying symmetry of the crystal. And what we'll do is exploit the anharmonic interactions of the crystal lattice, as I discussed before. But since we are interested in breaking the symmetry, the particular form of the interaction we need to use is different. It is a 3-phonon interaction instead of a 2-phonon interaction, which couples two different infrared active modes to a third Raman active mode. And from group theory considerations, if I want this one to be this one, I need to excite two infrared active modes that are degenerate and orthogonal to each other, one pointing along the a-axis and one pointing along the b-axis. And if I do that, a directional force will be imparted to push the crystal along this B2G Raman mode coordinate. Okay, and so essentially, and that will, as I discussed in the previous slide, generate a net magnetization just like you would with uniaxial strain. So essentially, in the end, what we need to do to achieve this type of control with light is to simultaneously excite these two modes and create the desired crystal structural distortion. So here I'm showing you the vibrational spectrum of cobalt fluoride. The two modes that we're interested in have a frequency of 12 terahertz. So what we need to do is just have an experiment where we use essentially terahertz pulse resonant with 12 terahertz. And if we have 2 terahertz pulses, one along A and B, we can simultaneously drive these two phonons. Luckily, we actually don't need 2 pulses because that can be quite difficult. Pumping along the A and B axis simultaneously is equivalent to just driving along the 110 direction. So that's actually what we do in practice. We have 1 terahertz pulse polarized at 45 degrees. And then we carry out a relatively simple experiment, which is a pump probe experiment where I first pump with my terahertz pulse, and then I'll probe with a second pulse propagating along the c-axis. And through the Faraday effect, the magnetization along the c-axis will lead to a rotation of the plane of the polarization of this probe pulse. And so what I'll do is I'll measure the rotation angle of this probe as a function of time delay, and I'll resolve then the pump-induced magnetization in the system. So when I carry out this experiment, this is what I see. I'm showing you here experimental data, which is a plot of the rotation angle as a function of the time delay. And the pump comes here at 0 time delay on the x-axis. And what you can see is that before the pump arrives, the rotation angle is 0, as you would expect for this fully compensated, unstrained antiferromagnet. And then after the pump arrives, we see a small change in the rotation angle. It increases and decays on the time scale of a few picoseconds. But this is not the whole story. Actually, if we zoom out, we see that the signal actually changes sign and gets much, much larger and reaches a maximum after a few hundred picoseconds. And this is, in fact, the magnetic signal that we're interested in. So how do I know that this is the magnetic signal that we want? Well, we did a couple of checks. One is that we carried out the same measurement on a similar non-magnetic compound, which is isostructural, zinc fluoride. We find no such long-term signal. Okay, we also find the same behavior when we carry out a pump probe circular dichroism experiment. Okay, so both of these confirm and indicate basically that when you pump this 12 terahertz mode, you get an induced magnetization that lasts on a time scale of a few hundreds of picoseconds. Okay, and so now we can try to understand this a little bit better. We track this pump-induced signal as a function of temperature. And what we see is that as we warm up the sample, the strength of the signal goes down. And if we extract what is the maximum signal here as a function of temperature and we plot it, what you get are these squares, and circle are the same measurements but from circular dichroism experiments. And what you find is that eventually the signal reaches 0 precisely at the nail temperature. Okay, and this is what you would expect from a piezomagnetic type of effect. And actually the temperature dependence of the induced Faraday rotation closely matches that of the static piezomagnetic response of the material. So this provides a confirmation that this idea of observing an analogy to the static piezomagnetic effect is valid. But this time what we're doing is actually driving that dynamically using optical phonons on a much faster time scale. So also an analogy with the static piezomagnetic effect, we should be able to switch the sign of the induced magnetization. And you can do that by just looking at the form of this interaction. And you can see that if we change the sign of one of these infrared active modes, then the force on this Raman mode should change sign. Right? So for example, if you pumped this mode in the opposite direction, we would create a force that pushes the Raman mode in the other direction and generates a magnetization in the other direction. And this can be done relatively easily by just changing the polarization of your pump pulse by 90 degrees. Okay, so let's see if this works. What I'm showing you here is the same data that I showed you before. And now I'll just rotate the pump by 90 degrees, where we now are going to drive the Raman mode in the other direction. And you can see that indeed the magnetization signal, this rotation signal switches sign. So this shows that we have a way of controlling the direction of the induced magnetization with just the incident light polarization. And so I think now the most interesting question remaining is how does the strength of this effect compare to the static piezomagnetic effect? So what we can do is crank up the peak electric field of our terahertz pulse from 1 megavolts per centimeter to the strongest that we can generate, which is around 12 megavolts per centimeter. And now if I look at the maximum rotation angle, I can see that first of all, the signal scales quadratically with the pump field. And this is expected if you look at the form of our nonlinear interaction, where the induced Raman mode, which is proportional to the magnetization, will be proportional to the two infrared active modes multiplied together. So this is another good check that our phonon-driven model is accurate. And the second thing I can do is now convert this rotation angle into an induced magnetization using the known magneto-optic coefficients of cobalt fluoride. And if we do that, we find that we can achieve a maximum induced magnetization on the order of 0.2 Bohr magnetons per formula unit. So now the obvious question is this a big number? Is it something potentially useful, or is it just something fun to do in the lab? Well, we can compare to what was achieved with strain. And so the largest strain-induced magnetization that is reported in the literature is only on the order of 5 × 10⁻³ Bohr magnetons per formula unit. So obviously, the effect that we see is much larger than that. But what if you stretch the crystal harder? What if you stretched it enough that it would break? If you did that, you would only be able to reach up to out here. So this is about 2 × 10⁻² Bohr magnetons per formula unit. And so what we were able to achieve is something that's about 100 times more than what would be statically possible. And it's equivalent to something like a 50 gigapascal uniaxial strain if you would extrapolate this data down here. Okay. And the important point is that this is really only possible by dynamically driving the crystal, getting into a non-equilibrium state and exploiting the nonlinear interactions between optical phonons to drive a specific structural distortion. And so if you think about it, I think this is very exciting. Basically, I showed that you can break an underlying symmetry and create, in some sense, a better magnetic state that you could do statically just by shining light on the material. So this is great. But one thing to note is that everything here was still below the critical temperature. We're still within an existing magnetically ordered phase. So an important question to be able to push this further and make this approach a little bit more useful is can we somehow extend this behavior to higher temperatures and induce magnetism above the equilibrium TC? And I'll show you now in the last part of my talk a very recent experiment, still unpublished, where we provide some evidence that you could do that. So the system that we looked at in this next experiment is the transition metal oxide yttrium titanate. And I'll explain to you why we chose this system in the next couple of slides. It is a rather unusual ferromagnetic Mott insulator. It has a Curie temperature of 27 Kelvin. And what's most important to know from a microscopic point of view about this material is that there is a single spin 1/2 electron that lives near the Fermi level, and it lives in this titanium T2G orbital manifold. This is the low energy electronic states that are accessible. And in this particular compound, the titanium, the T2G levels are somewhat split by an orthorhombic distortion of the crystal structure, but there is still a fairly large orbital degeneracy. Now, in this type of degenerate T2G system, one could see from simple good enough Kanamori type superexchange arguments that how the orbitals are arranged on the various titanium sites within the unit cell will strongly influence the magnetic interactions in the magnetic ground state. That is, whether the system will be ferromagnetic or antiferromagnetic. So just to break it down, if we expect in some kind of cartoon picture that if adjacent sites have different orbitals, or sorry, have the same orbital, then we would expect to have antiferromagnetic spin interactions. While if we had different orbitals on adjacent sites, we would expect to have ferromagnetic spin interactions. Okay, and so the situation is much more complicated in reality, but you can already see from here that there is some level of degeneracy that exists. And in reality, you will have to model this system with the so-called Kugelkamsky Hamiltonian, which is a correlated spin orbital Hamiltonian. And what that model tells us is that if we're in the cubic limit, you will have a highly frustrated system with highly degenerate ground state and strong entangled spin orbital fluctuations. And actually, this kind of good enough Kanamori picture breaks down in that limit. You can think of that limit as the system being somewhat of an orbital liquid, an analogy with a spin liquid. Now, in reality, in yttrium titanate, the orthorhombic distortion relieves this scenario and helps to choose a particular orbital ordering pattern, which then sets the ferromagnetic ground state of the system. But nevertheless, the spin, the orbital, and the lattice degrees of freedom are all very strongly coupled to each other in the system. And that has some very interesting consequences that have been observable in experiments. Okay. So One of the consequences is can be seen here. If just take a look at this phase diagram, this is from Takura's group from a long time ago, where they studied solid solutions of yttrium titanate and lanthanum titanate. And what you can see is that starting from yttrium titanate on the left side here, which is in the ferromagnetic state, as the lanthanum content is increased, which actually makes the system more cubic, less distorted, the ferromagnetic transition temperature goes down. And eventually the ground state of the system becomes antiferromagnetic. Okay. And you can also do something similar with uniaxial pressure. And so the magnetic order is very sensitive to the structural distortions of the system. Right. Another manifestation of the spin lattice coupling is that the frequency of specific phonon modes is going to be modified due to the presence of local spin correlations. Okay, this is the spin phonon, simple spin phonon coupling effect that's seen in many different types of magnetic systems. You can think of this as related in some sense to magnetostriction. But what's unique here is that the frequency shifts have been observed experimentally, not just below TC, as you would expect, but they set in around 100 Kelvin, which is nearly 5 times TC. And so what this tells you is that there are spin correlations, magnetic fluctuations at very high temperatures. And so this has been suggested to be a consequence of these entangled spin orbital interactions that I discussed in the last slide. So what we have is a strongly interacting system where magnetism can be tuned through the lattice, and the high temperature, and we have high temperature precursor fluctuations well above the ordered phase. So we can ask the question, can we optically control magnetic order and even stabilize magnetic order above TC by driving the high temperature precursor magnetic phase with light? So that's what we set out to answer. And so we designed, again, a very simple pump probe experiment, similar to the one I showed you earlier in cobalt fluoride, except this time we carried out in a reflection geometry using the magneto-optic Kerr effect. And the Moog signal that I'm going to show you here is proportional to the change in the magnetization that is induced by the pump. So here, to drive the lattice in a controllable way, we actually developed a tunable narrowband terahertz source, which can span essentially the whole range of vibrational frequencies in this material and also other complex solids. And so what we were able to do then is to pump various phonon modes and compare their dynamics. And what we're going to do is focus on 3 modes, one at 4 terahertz, one at 9 terahertz, and one at 16 terahertz. And these all have very distinct, qualitatively distinct atomic distortions associated with them, which change the octahedra in different ways. And so we can compare the dynamics of these and see what kinds of distortions we would expect to create different changes in the magnetic order. So we'll start with a measurement well below TC at 5 Kelvin. What I'm going to show you is the Moog signal as a function of time after pumping the different modes. And what's important to know before I show you the data is that a positive signal is going to indicate an enhancement of ferromagnetism, while a negative signal is going to indicate a weakening or destruction of ferromagnetism. And the data is shown here. In gray is where the pump comes, and in blue, yellow, and red are the responses that we find after pumping the different modes that are shown here on the right. And so what we find is essentially, depending on the phonon that we pump, we either get a positive or negative response that has different magnitude. And so this indicates that we can either enhance or suppress magnetization of the system on a time scale of a few tens of picoseconds. And it remains in this non-equilibrium state for up to several nanoseconds. And this depends on the specific vibrational mode that we drive. And this was already a pretty exciting result, as it's, I think, really the first time that phonon selective control of magnetism has been demonstrated in this way, which shows that really definitively that the actual type of lattice distortion that we drive is important, and not just the energy that we deposit into the system. Okay. So now what we're going to do is try to understand this non-equilibrium state a little bit better. And I'll focus on the 9 terahertz pump case first, which had the largest effect, and explore what happens as a function of magnetic field and the function of temperature. So first, I should show you the field-dependent magnetization in equilibrium. So here, I'm just showing you half of the hysteresis curve. This is magnetization as a function of magnetic field. And what you can see is that as you increase the magnetic field, the magnetization saturates quite quickly. And what's interesting is that even well below TC, so this is at 5 Kelvin, and at relatively large fields relative to the coercive field of the material, the magnetic moment saturates only at about 0.8 Bohr magnetons per titanium, which is significantly below the spin 1/2 limit of 1 that you would expect. And this suppression cannot be explained by spin orbit effects. It cannot be explained by canting of the magnetic moments. It's potentially related, again, to the existence of this sort of fluctuating spin orbital order, at least in theory. Okay, so what happens to this magnetization when we pump the system? Here I showed you that we can enhance the magnetization. So on the left, I'm just showing you raw time-resolved traces in different magnetic fields. We can convert these rotation angles into magnetization. And on the right, in blue, I'm showing you the total magnetization in the pump-induced state at long times. And you can see that this non-equilibrium magnetization now saturates nearly right at that spin 1/2 limit. So this is suggestive that we may be stabilizing this kind of fluctuating order. I think what's even more suggestive is the fluence dependence, which shows that this spin 1/2 limit here is really a hard limit, even when we increase the pump strength. So, this is again suggestive that whatever is suppressing the fluctuation, suppressing the magnetism at low temperatures can be relieved by pumping this particular mode. Okay, now we can track what happens as a function of temperature. Here I'm showing you again the equilibrium magnetization as a function of temperature. Here is TC, 27 Kelvin. And here, the total magnetization in the pump-induced state at long times. This is normalized magnetization, just so you can compare them one-to-one. And what you can see is that in this case, unlike the cobalt fluoride case, this pump-induced effect does not at all go away at TC. And actually, it can be observed up to much higher temperatures, at least 3 times TC in our current measurements. And if we look at the field dependence of this non-equilibrium magnetic state above TC, we find that it has a ferromagnetic-like spin stiffness. So here I'm just showing you the magnetic field dependence at around 60 Kelvin. And you can see that it has this kind of a ferromagnetic-like spin stiffness, which actually maps quite well onto what is measured in equilibrium just below TC. So this is 25 Kelvin. And so again, this is suggested that we've created a ferromagnetic-like non-equilibrium state that can exist at very, very high temperatures. And if you look at the temperature dependence of this non-equilibrium magnetic state, it follows relatively closely the short-range spin correlations that we found from the equilibrium spin lattice coupling measurements. Okay, so what is the origin of this pump-induced ferromagnetism? It's a complicated question based on dynamical spin lattice orbital coupling. But to try to answer this, we turned to our colleagues at Harvard and the Neuron Group, where they developed a theoretical framework based on the Kulikomsky model. And I'm not going to be able to go into details here, but what I can tell you is that there are basically 3 contributions that are important. One from the static crystal field, which is set by the lattice. Another, which is the usual, I would say, spin-dependent superexchange, and another spin-independent orbital superexchange. And the way we thought about explaining our data was to try to understand how the phonon excitation affects the orbital ground state, and how that in turn affects the magnetic system. Okay. And so first what we did was to calculate the equilibrium ground state of atrium titanate, where you can see the different orbitals on the different sites in the unit cell shown here. And you can parameterize the orbital states in terms of 2 so-called orbital angles, which parameterize the system based on the 3 T2G orbitals. And then what John Curtis at Harvard did was to consider a fictitious scenario, a thought experiment. What would happen what would the magnetic ground state be if we froze all the other degrees of freedom of the system and just varied the orbital angles by hand? Right? So not surprisingly, what you would find if you did this is that the magnetic order depends sensitively on which orbital angles you choose. And then you can make a kind of a magnetic phase diagram, which is shown here on the right, where the different colors indicate the different potential ground states. And here, these two axes correspond to the two different orbital angles, theta and phi. So most of this phase space is not physically accessible, but it shows you how complex these spin orbital interactions are. If you plot the equilibrium orbital angles onto this plot, you will get this black dot shown here. What's interesting is that this is really, it's in the ferromagnetic phase, but it's really, really close to the phase boundary with a competing low energy antiferromagnetic phase. And you can think of this as an origin of the magnetic fluctuations that I talked about earlier and that you find in equilibrium. So now let's zoom in to the region just around the phase boundary here. And again, sorry for the change in the color scale, but here now you can see quite nicely how close the system is to this competing antiferromagnetic phase. And now we can ask the question, what happens when we pump the system? Okay, so what we can do is calculate then what the driven lattice distortion does to the orbitals and how it moves us around in this effective phase diagram. Right. So when we do that, for the 9 terahertz mode, we find that the system is pushed farther away from the boundary. So what this would predict is that we would suppress fluctuations and strengthen ferromagnetic order as we see in our experiment. And now we can also do this for the 16 and the 4 terahertz modes. For the 16 terahertz mode, we see that the orbital state changes, but it doesn't really move appreciably farther away from the phase boundaries, so we wouldn't expect too much of an enhancement. And for the 4 terahertz mode, the orbital angles are predicted to actually push the system, closer to the phase boundary, therefore increasing the fluctuations and weakening the ferromagnetic order. Okay, and when you compare the temperature dependencies of all these pump-induced states, they all qualitatively agree with the theoretical model. We see a weakening for the 4 terahertz, almost no change for the 16 terahertz mode, and an enhancement, a strong enhancement for the 9 terahertz mode. Okay, so to recap, what this model is telling us, or what we extract from this model, is that the different phonon excitations essentially modulate the T2G orbitals of yttrium titanate in such a way as to amplify or suppress the influence of magnetic fluctuations, which weaken or enhance ferromagnetic order in equilibrium. And so in the best case scenario, what we've been able to find is that we can increase the effective transition temperature up to about 3 times. And again, I think this is a really remarkable result, which shows that driving the lattice can, in some sense, stabilize the fluctuating ground state. And you can think of this maybe in the context of high temperature superconductors, spin liquids, and other strongly correlated systems, which show these kinds of fluctuations at high temperature. Okay, so we'll see where this goes, but now I want to wrap up and give a quick take-home message. So what these examples showed, or what I tried to show, is that we are at a stage now where we can use light like a tool to rationally design material properties. And you can think of this as akin to other methods out there that are used to control quantum materials and realize new states of matter. But in some sense, I think light has some advantages because we're able to design properties that exist outside of equilibrium constraints. Of course, it has its own set of limitations, but right now I think we're just scratching the surface of what we can do and what we can learn, especially if we imagine combining together these different techniques. So with that, I want to make a quick advertisement before I wrap up, which is, as I said at the beginning, I'm moving to Cornell in July, starting a new group. So if there are any interested potential students or postdocs out there, please do not hesitate. Feel free to reach out to me. So with that, I thank you all for your attention, and I'm very happy to take any questions. Thank you.
Okay, thank you very much. Let's see, let me look in Q&A. Please type in the questions in Q&A or chat, and then I'll read them. Yeah, Yinging Wu asks, why is there a finite angle for antiferromagnetic states, question mark?
I think I don't understand the question. Do you mean like this orbital angle? I don't know if they can follow up on the.
If you could type quickly.
Yes.
Yeah.
Oh, okay. Yeah. Yeah. So this is just telling you basically that. Okay, let me go back to this picture here. So this is just telling you that depending on the orbital angles here, meaning here the orbital angle, the specific orbital angle tells you what type of ground state, orbital ground state the system is in, right? What combination of T2G orbitals the system is in. And the symmetry of the lattice dictates, well, what are the associated orbitals on the adjacent sides. So this orbital is different from this orbital, and it's dictated by symmetry what these two, how this orbital relates to this one. And so just by deciding what the orbital angle is, this should be, it's not a physical angle, it's just a way of parameterizing the titanium T2G state. But for some specific titanium T2G states, these two orbital angles are close enough that you will get overall antiferromagnetic interactions. Does this answer your question?
Seems so. A question also from Tae-hee Kim, is this technique manipulating magnetic order by phonon excitation working only for strongly correlated systems, question mark, not for transition metals, question mark?
So I think it's quite powerful in the context of strongly correlated systems, just because you have these phases which are very close energy with each other. So you can use just kind of small variations in the crystal structure to make very, very large changes. But it's not to say that you cannot use the ability to drive specific motions of the lattice to manipulate magnetic order. And so you can, in principle, also do something similar in transition metals. It should be noted that it's difficult to imagine doing this in, well, there are complications in doing this in metallic systems because you will absorb energy that will not only go into the phonon, but also go into electrons at low energy. So this is one problem. But you can imagine a very simple magnet where you have direct exchange that is dependent on the bond length between adjacent transition metals. And just by tuning this bond length, you can change the exchange interaction. So this is something that you could also imagine doing by directly driving the lattice.
Okay, good. Other questions? Type away quickly. I guess I have a question, and think if you had some application to say write a memory site by some new way using this kind of techniques, is there a way to push the frequency or the far infrared frequency more toward the optical or more toward the microwave, or what kind of materials would work for this kind of thing?
Yeah, that's a good question. I know that this is a strange frequency range for interfacing with either telecommunications or with electronics. So that has been actually one of the issues in this field for a long time, is developing those light sources. I think what you're limited by is if you want to use this particular type of effect, you need to be resonant with the vibrational modes in the crystal, which are always going to be in this terahertz range. So that's a problem. But one thing that some people are doing, which is an interesting route, is to try to imagine using on-chip terahertz type of excitations. So trying to make things like terahertz waveguides and integrating them with the photonic chips to essentially guide terahertz waves, strong field terahertz waves, and interface that with some magnetic material that you can put inside this waveguide. So it's a very niche system right now. It's kind of these are like bespoke type of devices, but I think if that type of device is mastered, you could imagine interfacing this with more conventional electronics at some point.
Sounds great. Another question from Yinging Wu. What is the laser spot size, question mark? Will the measured area be in multiple magnetic domains?
This is a good question. The laser spot size are typically on the order of 50 microns. It depends on the wavelength and your focusing conditions, but usually on that order of magnitude. Yes, if you're not careful and you don't train the system beforehand, you're going to definitely end up exciting multiple magnetic domains, which are going to make the essentially increase the background. You're not going to be able to resolve your signal. So what you have to do, and what we have done in all of these cases, is to put the system in a relatively single domain state by either cooling down in a magnetic field or cooling down under strain. And then the domain sizes are typically then large enough that we can excite a single domain at a time. Good question.
Oh, okay. Thanks very much. I think it's a fascinating topic, sort of takes me further than I would have imagined. So it's very nice. Well, thank you very much for giving the talk.
Absolutely.
Enjoyable.
Yeah, thank you again, everyone, for listening, and thank you for having me here.
Thank you.
Thank you so much. Bye.